Bonjour à tous. Alors, j'ai prévu quelques notes quand même pour présenter Francesco, que j'ai grand plaisir à écouter aujourd'hui. Donc, il est professeur à l'Université de l'Aquila. Merci d'avoir rien marqué sur ton slide, donc comme ça je peux me servir de mes notes. Il est directeur du MEMOX, Centre international de recherche pour la mécanique et la mathématique des systèmes complexes qui compte environ 300 membres à travers le monde aujourd'hui. Il est aussi professeur à temps partiel à l'Université de technologie de Varsovie. Et cette semaine, il est à D'Alembert en tant que professeur invité dans le cadre des visites prévues pour une période de 3 ans en tant que fellow ambassadeur du CNRS en mécanique théorique. Les thématiques de recherche autour de la problématique des material synthesis, comme ton nom l'indique, vont t'amener à nous parler du PPV, sujet que tu traites depuis une quarantaine d'années, on a eu l'occasion d'en discuter.
Tu le soulignes toujours.
Voilà. Et je vais souligner aussi que je suis presque sûr que tu vas nous parler de Truesdell aujourd'hui, mais on verra.
Ok, merci de l'invitation. Alors, je dirais une chose au début, c'est-à-dire que j'ai démarré à étudier les métamatériaux pour des raisons personnelles. J'ai un problème de vue et ma cornée n'a jamais bien marché et le cristallin aussi. Alors, sans entrer dans le détail, mais un cristallin, il est capable de se déformer avec les muscles qui sont autour de lui et grâce à ça, il change son indice de réfraction. Et donc, on peut mettre à feu à des distances très différentes avec un mécanisme très précis. Et imaginez-vous 5 millièmes de millimètre de cornée ont le même pouvoir optique qu'une dioptrie. C'est une chose énorme. Donc, il y a beaucoup de choses à faire. Et je vous dirai aussi une autre chose pendant la présentation des applications à la santé. Mais j'essaye de parler en anglais parce que pour rester dans le temps, je dois lire. Sinon, je ne suis pas capable de terminer dans l'air. OK. Donc, the principle of virtual work, a powerful tool for mathematical invention and for mathematical design. I like very much history of science, but we need it for getting tools for understanding new theories. So, mechanics is the first mathematized theory in history of science. Mechanica Problemata is an apocryphal text attributed to Aristotle. In it, the principle of virtual work is already applied systematically to predict the functioning of machines. The mathematical formalism on which it is based is the Euclidean geometry. It is the most ancient example of the unifying capacities of mathematical abstraction in modeling of physical phenomena. The ideas in Mechanica Problemata, via Latin and Arabic translations, are later transmitted to Lagrange and Piola. Vous savez que Lagrange était italien. Piola a écrit sur un principe controversé de la mécanique analytique de Lagrange. Le débat est ancien. Okay? Remark that mechanic is with the H. We believe that the Mécanique analytique by Lagrange is the most innovative treatise in the field after Mechanica Problemata. Remark that the word mechanics is a calque of the Greek word mechanica. Chi is with the H. The theory that it presents has been considered to be controversial since its appearance in 1788. This controversy continues until our days. All results in Mécanique analytique are obtained starting from the principle of virtual work. We have a kind of grand unification theory. Okay. Clearly, Mechanica Problemata is a primary source for D'Alembert. Il faudrait bien comprendre dans le travail des encyclopédistes, probablement la connaissance de l'ancien grec était très bien considérée. Et je pense que D'Alembert a lu comme livre de texte le Mechanica Problemata. C'était étudié à l'université. A system is in equilibrium when the total work done by all interactions involving the system is 0 for each virtual displacement from equilibrium. If the principle of minimum energy holds, then the consequent stationarity conditions imply a particular form of the principle of virtual work. People do not understand why virtual displacement. But think about minimum. What you do with minima. You have a candidate minimum, you change a little bit the independent variable, and then you test if the function has a greater value or not. So the idea behind virtual displacement is exactly the idea behind the concept of finding minima. Therefore, the postulation based on the principle of virtual work is more general than that based on the energy minimum. Lagrange statement is very general. Now, I read only bold words. Why? Because Lagrange did not use vector algebra. If you don't have vector algebra, you have only geometry, then you need the extra words. Okay. If a system is in equilibrium and if a small movement is imparted to this system, then the sum of the powers multiplied by the distance will be equal to 0. Lagrange statement can be reformulated even for founding continuum mechanics by using the abstract language of functional analysis and theory of distribution. Now we have a nominalistic issue. The word power, as used by Lagrange, means what we call force. He wanted to change the nominalistic assumption, the choices, okay? Of course, I will not resist here, and I will tell you that Truesdell, reading power without reading the definitions, decided that Lagrange was completely wrong. Okay? Now, in every book of mathematics, you must read the definitions before going to the formulas, right? Okay. Although a modern formulation of this principle usually includes the use of concepts from functional analysis, tensor algebra, and calculus, one has to agree on these points. Lagrange's formulation seems so general that it includes all the versions that have been formulated so far, and second, it uses the minimum possible mathematical concepts, only Euclidean geometry, that are sufficient to rigorously express the principle in its full generality. On the contrary, Truesdell in 1968 states that the Lagrangian mechanics would have a very limited scope. Okay, granted its more modest scope, estimates of Lagrange's performance must remain a matter of taste. Hamilton's praise of the Mécanique analytique as a kind of scientific poem is but it is unlikely that many persons today would find Hamilton's recommendation in non-scientific poetry congenial. By the way, Truesdell has this Baroque way of producing sentences which make them very difficult to understand. With a Baroque language, he manages to criticize Hamilton, who had called the Mécanique analytique a scientific poem. However, we believe that the style of Lagrange is so clear and modern that one can read it profitably also today. It can be considered in many parts to be a modern textbook. I could read it and it is a pleasure. the French by Lagrange is clear, and the ideas are exposed in the best possible way, I think. Okay. Now, Lagrange's best ideas in mechanics derive from his earliest period, when he was studying Euler's paper and had not yet fallen under the personal influence of D'Alembert. Therefore, if one trusts Truesdell, Lagrange were a Pinocchio under the influence of the bad boy D'Alembert. By the way, Euler derives the equation of Elastica with a variational principle. So really one cannot understand why Truesdell, who wants to use only balance of forces and balance of moment of forces, prefers Euler to Lagrange. This is a mystery. Okay, analytical mechanics induces the belief that discrete systems and rigid bodies exhaust the universe of mechanical discourse. In 1788, the mechanics of deformable bodies, which is inherently not only subtle, more beautiful and grander, but also far closer to nature than is the rather arid special case called analytical mechanics, had been explored only in terms of isolated examples, brilliant but untypical. Unfortunately, most of these fitted into Lagrange's scheme. Those that did not, he passed over silence. This is what he writes. This commentary shows that Truesdell had not read the last chapter of Mécanique analytique in the version of 1802, and the works by Piola, albeit he cites them systematically. To understand the personality of Truesdell, this is the painting which was in his dining room in front of the main sitting place of the host. Paul Germain told me the story that he was obliged to eat, having this lady sitting on his right and naked in the painting. Okay, so this gives you the idea of du personnage. Okay. Now, forces or work. Truesdell claims that mechanics is to be founded on the concept of force. He claims that balance laws, and in particular boundary conditions, can be induced from experiments. Instead, D'Alembert was persuaded that the most fundamental concepts in mechanics has to be played by work. Here I have a pseudo-Einstein quote. I could not find it anywhere, but many people are attributing it to Einstein. There is never enough experimental evidence that can prove that I'm right, while a single experiment can prove that I am wrong. Okay, so Truesdell is in a sense a follower of Francis Bacon. He is an inductivist. Okay. D'Alembert believes that the principle of virtual work must be postulated a priori, and its logical consequences are the predictions to be experimentally checked. The force is a derived concept used during the logical development of the theory. Of course, very useful in many applications, but without any direct experimental counterpart. According to D'Alembert, the fundamental and unifying idea has to be found in the principle of virtual velocities, later renamed principle of virtual work. In Greek, you find in the text principle of virtual velocities. They have in mind the fact that you change a little bit the equilibrium configuration or the motion. Okay? Les forces inhérentes au corps en mouvement, êtres obscurs et métaphysiques qui ne sont capables que de répandre les ténèbres sur une science claire par elle-même. J'espère qu'ici, dans l'Institut d'Alembert, personne ne va m'attaquer pour ça. Mais, vous savez, la folie humaine, elle est remarquable. Je dois avertir que Pour éviter les circumlocutions, je ne me suis souvent servi du terme obscur de force et de quelques autres qu'on emploie communément quand on traite du mouvement des corps. Mais je n'ai jamais prétendu d'attacher à ce terme d'autres idées que celles qui résultent des principes que j'ai établis. In other words, primitive concepts are kinematical ones. You postulate the principle of virtual work, then in this framework you define auxiliary concepts, mathematically you define them, and you call them force, for giving to them a name. By the way, yesterday I had a discussion of a true French scientist. When I said force, he said, I refuse to talk with you. I only understand what power is. Also, I immediately switched to the other language. So, who was the true author of Mechanica Problemata? Why Dell'Isola has this fixation with history? There is a first answer. Archidas of Tarentum, many times cited by Archimedes. His other works are unfortunately all lost. He founded mechanics on the principle of virtual work, as done later by Lagrange and all the others. Archidas is believed to be the founder of mathematical mechanics. The source is Diogenes Laertius, and Plutarch, this is an old story, reproached Archidas for having contaminated geometry with mechanics. You know, there is always this problem between mechanicians and mathematicians. Okay. He became a statesman, and he uses the first formulation of the principle of virtual work in what is the first mathematized text of applied mechanics. Why are we so much interested in understanding how mechanics was at first formulated? To get hints about inventions, method for novel theories. I have a bad news, we all know it. There is no algorithm for producing modern, new, original theories. Of course, soon or later, artificial intelligence will do the job for us. Look, I am Epicurean. Your brain is a set of atoms, okay? Now, somebody calculated that something whose complexity is like your brain, your brain is not so much complex, but has to be a building 40 stores and a side of 40 meters. And all this has to be a computing system. Of course, these estimates are not serious. I mean, it depends on what you mean with interconnections and things like that, okay? So, when we will have computing machines like that, maybe they will be able to invent novel theories. Until then, we must invent theories in the only available way, reading what has been done by our predecessors, okay? And here I invest few of your minutes of your time. I invite you to go and study the whole history to talk about Archimedes on the method, which has been found in this palimpsest there. The text has been scratched away because it was difficult mathematics, and they wrote in the other directions some very practical and useful prayers against flu. Thanks to God, the ink used for writing mathematics was based on metal. So with X-rays we can read it. And what we have read there, Archimedes to Eratosthenes, greetings. I send you on a former occasion some of the theorems discovered by me, merely writing out the enunciation and inviting you to discover the proofs, which at the moment I did not give. The enunciation of the theorems which I send you were as follows. integral between a and b of s squared dx equal b cubed over 3 minus a cubed over 3 with a sequence of Riemann sums. So he did this. The proofs then of these theorems I have written in this book, and now I send to you. And now you see that also Eratosthenes and Archimedes were quarreling. By the way, Archimedes was calling Eratosthenes beta, to understand that he was alpha. Seeing moreover in you, as I say, an earnest student, a man of considerable eminence in philosophy, and an admirer of the mathematical inquiry, I thought fit to write out for you and explain in detail in the same book the peculiarity of a certain method by which it will be possible for you to get a start to enable you to investigate some of the problems in mathematics by means of mechanics. This is a word-by-word translation from the Greek. This procedure is, I am persuaded, no less useful even for the proof of the theorems themselves. For certain things first became clear to me by a mechanical method, although they had to be demonstrated by geometry afterwards, because their investigation by the set method did not furnish an actual demonstration. Archimedes understands very well that objects which are in the physical world are different from objects in mathematical world, and mathematics is modeling parts of reality. And you cannot prove a theorem with an experiment. Okay? But it is of course easier when we have previously acquired by the method some knowledge of the questions to supply the proof than it is to find it without any previous knowledge. Then it tells that Democritus and Eudoxus share the name of a theorem conjectured by Democritus and proven by Eudoxus. Okay, I am myself in the position of having first made the discovery of the theorem now to be published, and by the method indicated, and I deem it necessary to expound the method, partly because I have already spoken of it, and I do not want to be thought to have uttered vain words, the proudness of the big scientist, but equally because I am persuaded that it will be of no little service to mathematics, for I apprehend that some either of my contemporaries or of my successors, and we are his successors, will, by the means of the method, when once established, be able to discover other theorems in addition, which have not yet occurred to me. So, okay, we can go ahead and we simply tell here that the barbarian Roman kills the sophisticated Greek, but, you know, Romans had invented democracy, the true one, the one with rules and constitutions, while Greeks could never find a way for getting such an organization. Syracuse was lost by Greeks and Greek culture in a war where one Greek died for every 20 Romans. How this was possible? Because the party against Hieron in Syracuse opened the doors to the Romans. The political enemies of the tyrant decided that the city had to be given to the enemy. So the invention of Romans is the democracy, the one with rules. Okay, so Archimedes had cleared the distinction between a mathematical model and physical reality, and he knew that no theorem and no postulate can be proven experimentally. Is it worth to ponder about this epistemological and historical debate still nowadays? Is mechanics, the most ancient among mathematized theory, still fertile of theoretical problems, and is it still effective in supplying the needed guidance in technological applications? The answer is yes. In fact, one must refrain from the inductivistic belief that laws of physics can be induced from experimental evidence. Think about Bertrand Russell chicken, whose neck was wrung the day in which he formulated the physical law, I am fed every morning 7 o'clock. Okay? What is interesting is that this inductively justifies the conclusion that induction cannot justify any conclusion. It is very, very nice by Russell. An example of good epistemological practices in continuum mechanics is given by Paul Germain. He was the man who formulated the principle of virtual work in the language of the theory of distributions. He recognized that functional analysis had to be used in this context, but at the same time, he was the man who designed the wings of Concorde, being the head of Onera. Okay? And you find this only in France, I think. Somebody who knows what is a Sobolev space and at the same time can do serious engineering. Okay, I hope you will not change your system because we could have troubles otherwise. Okay, we can say that the principle of virtual work remains the most powerful tool to be used to favor scientific creativity and also to push the technological advancements in mechanics. Here we will illustrate these statements by discussing how it is essential in the modern theory of metamaterials or architectured materials. First example is given by the negative Poisson effect materials. The microstructure has been fully discussed, I show you on the right, but here I want to underline for you that Lamé and Green managed to prove logically the existence of negative Poisson effect using the energy, an energetic approach. Okay, so the debate about the existence or non-existence of negative Poisson effect has been solved using variational methods. This is the second application of metamaterials, which is touching my family. My father had 1 meter of these Gore-Tex tubes inside his body for 25 years. So instead of dying 70, he died 93. This material, when you pull it, elongate it, enlarges its section. So this is a typical Gore-Tex artery prosthesis. And Milton Greme and Andrei Cherkayev designed a material whose properties are very unusual. In the reference configuration, it seems to be a solid. You apply small deformations or forces or displacements, it behaves like a fluid. It is not capable to sustain shear forces. And then in large deformation regime, it behaves like a solid. Okay? So the fundamental problem in metamaterial synthesis requires a Kuhn change of paradigm. Okay, I know in English you call it paradigm, but I cannot do it. The fundamental problem in the theory of metamaterials consists in the synthesis of materials having some specific physical properties. While up to now one looked for the equations describing a specific already existing material, instead in metamaterial theory one chooses the equations mathematically representing the desired behavior and then looks for the microstructure that, once homogenized, is at macro level governed by the chosen equations. So the problem is solved in 3 steps if we follow Gabrio Piola intuition. First, the choice of the continuum theory describing desired behavior, valid at macro level, via a judicious choice of macroscopic descriptors and a suitable formulation of the principle of virtual work. So you have the target macro model. Then you conjecture in a specific class of microarchitectures having a multi-scale structure the subclass which is candidate to be governed by the chosen macro model. And finally, the identification of the macro constitutive equations in terms of the suitably parametrized micro properties in the selected subclass of microarchitectures by identifying micro virtual work with macro virtual work. Virtual work is a scalar. You can identify. How you identify micro forces with macro forces? This is a nightmare. Therefore, the conclusion of the epistemological debate gives us a powerful tool for conceiving and producing new real-world materials. Landau, Lifshitz, Feynman wrote in different moments of their life that the only way for inventing new theories is to use variational methods, energy-based methods. The micro-macro identification becomes very difficult if one uses models based on balance of forces and balances of moment of forces. In fact, at macro and micro level, one usually needs different sets of kinematical descriptors and therefore different balance postulates. Okay, so even if you want to use Ehringen approach to generalized continua, postulating balance laws for every kinematical descriptor, it is very difficult without the a priori knowledge usually given by variational principles to understand which micro balance laws contribute to a certain macro balance laws. I gave here my first seminar in the far 1986, okay? And I had discovered French viewpoint after 3 years of nightmare because my PhD supervisors wanted me to deduce capillary fluids equations using balance of forces, which is a work without any hope. Then I visited Pierre Sepecher in Toulon. I met Pierre Casal in Marseille. I gave a talk here invited by Madame Catignol, and we presented them our way of micro-macro identification based on this procedure. Okay. Now, Lagrange statement, which we already have seen, can be formulated in the language of virtual work functionals. So soon I will tell you ideas about how the theory of distribution can be used in this context. And I want to state explicitly that the principle of virtual work is the only one which allows to us to get a standardized homogenization procedure from micromodels to get suitably descriptive macromodels. So even if there are some repetitions, I want to show you this scheme. First step, you choose macroscopic descriptors and macroscopic theory. Second step, for one given macroscopic configuration, you choose one microscopic representative. There are many microscopic state configurations which correspond to your macro, but you choose, this is an art for the moment, you choose the one you believe it is the more meaningful. Then you identify macro and micro work functionals, and as a consequence, you get macroscopic equations in terms of microscopic properties. Virtual work functionals are distributions in the sense of Laurent Schwartz. Virtual displacements are test functions. So we accept the postulates. The powers expended by the actions exerted on or exerted in a subbody are distributions concentrated on the body in the sense of Schwarz. These three theorems are very useful, and I will show you applications of them. Every distribution having compact support can be represented as the sum of a finite number of derivatives of measures, all having their support included in kappa. This will give us an idea how building internal power, internal work functionals. Then you can say that a distribution has order smaller or equal to kappa, and then every distribution having support included in a regular embedded submanifold, Cauchy wants actions on surfaces. So we need this theorem, can be uniquely decomposed as a finite sum of transverse derivatives of extensions of distributions defined on M. Now, the idea at the basis of Piola homogenization requires the choice of two classes of macro and micro virtual work functionals defined on the set of micro or macro admissible virtual displacements. So you choose the test functions at the two levels, and the equivalence class of micro deformations corresponding to each macro deformation. Okay? When you identify micro and macro work functionals, you have obtained your macro description in terms of micro structure. Now, look at the expression 8. This is a generalization of internal power functional which Cauchy has introduced for us. When n is equal to 1 and t0 is equal to 0. Now, if somebody asks you why you want to study this functional, the answer is obvious. Every distribution is built in that way. So if your postulate is that work functional is a linear, continuous functional on the test functions, Lorentz-Schwarz tells you that you must study this structure of functionals. Okay? And naturally, you are led to consider n gradients of the virtual velocity. Okay? So given, Piola calls these nth order continua. He studied these things in 1848, so it is an old theory. So given the internal work functional performing subsequent integration by parts on the domain boundary faces. Now, I'm using a polyhedron because I want edges and wedges, okay? Then I do it on boundary edges, and I end on boundary wedges at the end of this integration by parts, and using that the internal power must to be equal to the external power, clearly we obtain a final result, the class of admissible external interactions possible for a given continuum. There was a terrible debate between Piola and Poisson. Poisson said that external boundary conditions can be found experimentally. Okay, the answer of Piola is, are you applying shear forces to an Euler fluid? Why you are not? Because the energy of an Euler fluid depends only on the actual mass density. So your assumption about the deformation energy implies modeling limitations. You cannot study a fluid as distinct from Euler fluid. Euler fluid is a mathematical model. A fluid is a real object, and Archimedes is not confusing to do the two. So we should not do this confusion, okay? depending on your model, you can describe or you cannot describe some externally applied forces. For fluids, Euler fluids, you cannot describe shear. So what they do, they introduce either dissipation. So you claim that if you apply shear forces, the fluid starts moving, or capillary fluids, studied by the Nobel Prize, French Nobel, Pierre Dejean, okay? And you introduce the dependence of the deformation energy on the gradient of mass density. Now, with Pierre-Sepécher, we made this terrible integration by parts in the case of nth gradient fluids, and we have proven that an nth gradient fluid, nth gradient material, continuum, can sustain the dual of velocity in the volume B. So this one, okay, this one. Then it can sustain a force per unit area. It can sustain a force per unit edge. I call force the dual in power of the virtual velocity. So my definition of force is an element of the dual space of the test functions, okay? In the theory of distributions, it is a very well-defined object. But, and the theory of Laurent-Schwartz gives us the conceptual support of that, you are left with the dual of all normal gradients of velocity, virtual velocities, up to the order n-1 on the boundary, the dual of every normal gradient on the edges, and you have, when j is equal to 0, you have a wedge force, and you have up to n-3 duals of the gradient. The transverse gradient in a point is the gradient, okay? So these are the generalized external forces which can be applied to an nth gradient material. Okay. I recently published a paper where we start studying what happens in a crack when you have the edge and you apply a force. So I think that we can solve many paradoxes of J integrals with generalized forces like that. Okay, but at the end of the story, boundary conditions cannot be induced experimentally. When you start your postulation choosing a particular class of internal work functional, you have the class of external forces which can be applied. So when you think about the tetrahedron argument by Cauchy, you immediately understand when it can be applied and when it cannot be applied. You can apply the tetrahedron Cauchy theorem only when your external forces applicable are forces per unit area. Full stop. You cannot have edge forces or wedge forces. Why? Because in Cauchy tetrahedron argument, these are 0. Okay? Okay, Truesdell should, he died. So I want to say he should try to understand this. Truesdellians should try to understand this. Okay, I don't know if they will ever manage. By the way, Paul Germain, who was a wise man, when I told him all these things, he told me, keep quiet. It is impossible to persuade them. Go ahead, do your work and don't worry. Okay, now the problem of synthesis is not new. It is a pity that Corrado had to leave, because with him in the past we used the fundamental theorem in the synthesis of analog computers. You know, before digital computers, analog computers were used for solving partial differential equations using electric circuits. The theorem in the synthesis of analog computers is the following. Let us call elementary circuital elements resistances, inductances, capacitances, and transformers. For every quadratic Lagrangian and quadratic Hamilton-Rayleigh dissipation function, it is possible to find a graph, and for every branch of the graph, an elementary linear circuital element, such that the obtained circuit is governed by the corresponding Lagrangian equation. So, how do you solve a problem of synthesis? You find a minimal set of elementary substructures, you find a class of functionals, and then you try to build this functional using the energies relative to the fundamental elements. Okay, did anybody among you complain with persons expert in theory of circuits because they talk all the time about resistances, capacitances, transformers, and inductances? No. So please, don't blame me if I talk all the time about pantographs. It is not because I became senile. I have a conjecture. I can't prove this conjecture completely, but I will show you some interesting results towards this proof. I conjecture that using pantographs and using few other structural elements, I can synthesize every nth gradient continuum. Okay? Now, let us understand why this pantograph allows us to synthesize a second gradient material. Okay? Consider blue points. These are Piola points which we follow in our macro model. Red points are not described by the macro model, but are auxiliary for your micro deformation mechanism. When you elongate this pantograph, you have, if the pivots are all perfect, you have a deformation with zero energy. So nobody can tell you that second gradient deformation energy is negligible with respect to first gradient energy. First gradient energy is zero. Okay? So Trussdellians cannot repeat this song all the time. By the way, in Italy, but I'm afraid also in France, you have different professors for structural mechanics and mechanics applied to machines. Now, this theory shows you that the two theories are artificially separated, because at micro level you have a machine, at macro level you have a second gradient material. So, in the idea of Italian legislator, you need two professors for writing this paper. One in mechanics applied to machine, and the other one in structural mechanics, because we have distinct scientific groups. Luckily, here in France, you have mécanique, and life is simpler. Okay, you can have a truss version of the pantographic module. How did we get it? We synthesized in 2003 with Jean-Jacques Alibert, Pierre Precede, this energy which you see written on up. You have the standard Euler energy with U2 transverse displacement and U1 axial displacement, but you have the second derivative of axial displacement, which is new. It is higher gradient. Okay, now with suitable, following the process which I have described you in general, we have proven that this energy is synthesized with that microstructure. Then, very painfully, using hanky discrete models for Euler beams, so you have springs for elongation, and I hope you can see the red and blue rotational springs which describe bending, okay? Using an intermediate step in homogenization. So you have beams, then you have spring model level, meso level, and then you have macro level. We could prove that the deformation energy, and we have the theorem of that with gamma convergence, the deformation energy depends on theta prime square, the curvature in the plane of the beam, multiplied times a functions where the elongation rho appears. So you have a bending stiffness depending on elongation, and you will see a beautiful effect of that later. And then you have rho prime, so a derivative of elongation, multiplied times another function of rho. Okay? Then we invented third gradient transverse beams using the Warren bridge structure with at the top of it a pantograph. Okay, and we needed 8 years for doing it in 2011. One of the reasons for which I'm looking for young PhD students is that it is clear that I soon will die and I will not be able to complete all the work I need. You know, I believed to be able to do all this in 5 years, 25 years ago. Okay, when you find a micro-macro identification, you give an interpretation of the boundary conditions in terms of microstructure. Look, what is a double force at micro level? It is the force in green, which is represented there, applied to the two blue dots there. Resultant force 0, resultant moment 0. No way for describing this in Trussdellian postulation. Okay? Paul Germain call it double force. And we call it reactive double force because you have a constraint and you have the corresponding Kirchhoff reactive double force. Then we synthesized an energy made of a system made with fibers with shear shear energy relative to the relative angle of the two fibers, and the synthesis was by the way, remark that this energy is incomplete. Only 2 second order partial derivatives appear. And the synthesis is this micro architecture. You have only one floppy mode, which is a zero energy first gradient deformation. When you impose suitable boundary conditions, you have beams which are bent. So this example gives you a beautiful example of how getting at macro level second gradient effects. Because at micro level, you have beams. Okay, then in a delirium of omnipotence, we did what? A pantographic structure where every fiber is a pantographic beam. But unfortunately, this energy is not yet complete. You lack some mixed order derivatives. I'm working to add a third family of pantographic beams for getting this. We are very close to the synthesis of the complete plate of second gradient in in-plane displacement. So we have a generalization of Sophie Germain Lagrange theory of beams. Look how beautiful is this synthesis. You have all pivots are perfect. You have the vertical, horizontal order of beams. This is a zero energy deformation. This is another zero energy deformation. This is another zero energy deformation. Okay? So, we wanted to study large deformations of that. Meso model with springs, okay? And okay, I will show you the energy later. We have a problem. Can we prove theorems without all higher order derivatives in the energy? In that moment, I hoped I could oblige Viktor Eremeyev to prove with me a new theorem. Then we discovered, and we published the result in the Journal of Elasticity, that a Russian called Nikolsky had invented the so-called anisotropic Sobolev spaces, which are doing the job for us. Okay, so we have found the first application of Nikolsky anisotropic Sobolev spaces for studying these generalized planar continua. Of course, you must block floppy modes to get well-posedness results. In the theory of elasticity, what you do, you block rigid body motions. In this theory, you must block also floppy modes if you want existence and uniqueness in the linear case. Then I want quickly to tell you that the identification, macro identification procedure has a very astonishing property. It is valid in the first case you see in that picture. And this is a mystery for me. It should be valid when the size of the cell is small enough, while we have proven numerically and experimentally it works very well, even in the case of wide knit. Okay. Did everybody here study Sevenin solution of the bending of a beam? I hope yes. Did everybody identify Euler theory of beam with micro-macro identification in energy based on Sevenin solutions? Also, we are teaching these things to our students. Okay. The micro-macro identification process gives a fundamental reason for the introduction of functional concepts in continuum mechanics. It is stronger than me here. I must say that on ne trouvera point de figure dans cet ouvrage. Everything is algebraic in a serious mechanical theory. Okay. Now, you have Sevenin anticlastic deformation of transverse sections. In Paris-Saclay, with François Hild, we have measured, this is not a computer simulation. These are measurements. This is a body which we built, which we deformed, and whose deformation we have measured using tomographic, the tomograph in François Hild's laboratory in Paris-Saclay. Look the strange deformation of the section. It is not anticlastic. It is counter-anticlastic, okay? And with this experimental device, you can go inside your specimen. You can look, darker colors are where the density of the polyamide is higher. And you see the pivots, you see the mechanism of the pivot. Look, when you pull from the top, the bottom line remains nearly undeformed because of the arch effect. So this metamaterial, which has been invented simply for synthesizing a second gradient material, proves to be very effective in absorbing impacts. Okay? But just to show you what you can do with these tools, this is a dream. This is a dream for mechanicians. You can see everything what happens in your body. And we wanted to recover also we wanted to recover also Cauchy cuts. Okay, so of course this movie I cannot control, it was pre-prepared, but I wanted to show you that you can see all the movement of all beams, twisting of the beams and everything like that. But look, you can have Cauchy cuts and never measure forces per unit area. You measure the deformation of the surface which you are showing with your Cauchy cut. So you can establish the state of deformation in every sub-body of your body and at its every surface. Look, in Berlin, we made, in the laboratory of Wolfgang Müller, we have proven that a pantographic beam behaves in a certain range of this point displacement like an Euler beam. Then you have a phase transition and it starts behaving like a cable. So you have a beam which after a certain range of deformation regime becomes a cable. Okay, this is a very exotic. We have printed also bipantographic sheets. Pivots, perfect pivots could be printed directly using the modern technology, and we have also done these measurements. And you can see the exotic behavior of this maillon pantographique. Okay. On dit maillon pantographique? Non? Textile. Comment on dit en français? Tissu pantographique? Tricot pantographique. And we implemented normal derivatives boundary conditions in the 3D printing. Okay? Somebody said, your system is not showing the same effects if you change the scale. So using a new device, multi-photon lithography, we could print small 20 micrometers pantographs, and we tested them, and we could also test millimetric pantographs, and the results which we obtained are very interesting, confirming what we have observed at the macro level. Look at this B1, B2 column. Changing the diameter and the height of the elastic pivot interconnecting the beams, you can have 2 times the force with essentially the same specimen. So a small change in the volume, less than 1%, produces a material whose capacity to resist to externally applied loads doubles. And this is exactly what we have observed with complex structures. So the reduction of the macro properties to the properties of this cell is proven, completed. I cannot resist, I've shown you some pictures which I have made myself. These are the pictures of the perfect pantograph on the right, which has been printed with polyamide. On the left, you have a metallic specimen. And I want to conclude with a further evidence against inductivism. I am nearly done. In large deformations, it is very difficult to recognize where a material subbody individuated in the reference configuration is placed in the present configuration. Okay? Using second gradient macro theory in the first row, or first gradient micro theory, second row. By the way, finite elements for the first theory are 1000 degrees of freedom. If you want to do a micro-theory first gradient in detail, as done in the second row, you need millions of degrees of freedom. Computation time of days, okay, but we did it. We predict where each subbody should be placed. And we look for this subbody in the image obtained experimentally, having also taken into account its predicted change of shape. The theory suggests where to find what we are looking for. Okay, this is against inductivism. Now, I don't believe that François Hild is an atypical product of the education system here in France. He is an experimentalist who has conceived this way for designing an experiment. It is his design, not mine. So as we could not track large deformations using his algorithm, he decided to guide his algorithm with our theory. Okay? Somebody should tell this to Trussell. However, the measurement is not influenced in any way by the conjectured theory. Okay, now I show you quickly what you can do. Multiphysics metamaterials, piezoelectromechanical microarchitecture. You have a plate, a set of piezoelectric actuators, the analog electric circuit on the other side, and you get a beam which is oscillating together in alternance with the electric circuit. Here we added dissipation, and we did the same also for plates. So this is the first electromechanical mode, the second electromechanical mode, an hammer strike, and then we added the damping, and in the optimal time we could damp the vibrations. So you should not believe that metamaterials are purely mechanical. You can invent also multiphysics metamaterials. And actually, with Joël Pouget, we started doing this many, many years ago. Okay. Now, different scales, different models. If your length scale is 10 micrometers, you need quantum mechanics or something like that. 10 micrometers, isotropic Cauchy model. 1 millimeter, Euler beam theory. 5 millimeters, second gradient theory. Your scale gives you the best, most adapted theory. Okay? And the reason for which I like Paris very much is mainly le Musée d'Orsay. I don't know, I go there. You know, if you come to Napoli and you visit the Archaeological Museum, National Archaeological Museum of Napoli, it is better than Louvre. I know that you are very upset for that. But come to visit the Archaeological Museum of Napoli, you will see beautiful things, which cannot see here. But le Musée d'Orsay is really unique. And you find there la nature se dévoilant à la science. Seulement en France, vous avez cette idée de la science étant une très belle femme qui vous montre son corps, okay? Et comment la persuader à vous montrer, se dévoiler? Il faut utiliser les principes variationnels. C'est la méthode que je vous suggère. Ok, Boris, tu ne dois pas dire à ta femme Lagrangienne, ça ne marche pas. Hein? Ok, merci de votre attention. J'ai fait seulement 1h10.
Thank you very much for the presentation, the historic concept, the context, and the philosophy that goes through. I have two questions. You mentioned that the variation, the principle of virtual power is more general than an idea of minimality, and I would like to know more. And second question, in a situation in which there are multiplicity of solutions, what does the virtual work principle say? How to...
No, okay, this is a debate. Anyway, you are touching a very delicate issue. Okay, I try. Helmholtz has proven for finite dimensional systems that there are evolution equations which are not Lagrange equations. So you may believe that there are systems for which the principle of virtual work is not a minimality principle. Okay? And strictly speaking, this is true. However, Landau and Feynman have written, you know, these people were like that. Landau wrote, n gradient continua, you can calculate easily. You know, he leaves it to students, and we needed a life for getting the result, okay? Feynman writes, I try to tell you the idea. Take a system governed by an evolution equation. Choose a higher order system with more degrees of freedom. Write a suitable Lagrangian in this larger space. Project your components somehow in the old degrees of freedom. You will find for a finite time period a Lagrangian which gives you the same evolution equations. Why I need to say that the time interval has to be finite? Because there is a Liouville theorem telling you that if you wait enough time, the system goes back to your initial conditions. However, the return time is usually longer than the time of life of the universe. You know, mathematics is giving you very strange results. If you have a box, you place on the left a gas, you have a diaphragm, you take away the diaphragm, Liouville theorem tells you that the gas will go in future all on the left, following its evolution. However, you need to wait Poincaré time, and this time is very long. So the idea of Feynman is you can reduce every system to a Lagrangian system. So you can reduce every virtual work principle into a minimizing principle if you choose a time interval and you choose a suitable Lagrangian. The bad news is that the Lagrangian is even not unique. Okay? So the relationship between minimizing principle and virtual work or virtual power principle is debated, and the reason for which, go and read Lagrange, the reason for which Lagrange says I formulate the principle of virtual work is that I don't want to discuss when something is Lagrangian. Okay? So this was the idea. So for sure the principle of virtual work is more general. Maybe it is equivalent. So this is your first question. I bet that you wanted to, you have been surprised by this simulation. Okay, look, this one,
The question was about multiplicity.
this is multiplicity, because if I manage to stop this, why this not? Okay. Here we impose this displacement. And for this level of force, you have 3 displacement exerting the same force. Okay? Lagrange writes somewhere these visionary words. If you want well-posed problem, impose all the time only displacement. So the problem of multiplicity arises when you are imposing problems where you give externally applied forces. So the problem of multiplicity is solved if you impose essential boundary conditions. Of course, I have no theorem for that. I mean,
Buckling beam with imposed boundary conditions has 2 at least solutions, at least 2.
Yeah, but you are we are talking about motion. In order to have well-postedness, you need to give initial conditions. So, of course, you have multiplicity of solutions. There is no problem, neither for energy nor for the principle of virtual work. You have 2 minima, and you have 2 configurations in which the work done is 0. There is no problem for that. Now, I believe you were talking about evolution. Thanks a lot.
Merci beaucoup.